Okay, this is the second video of vestibular function 2. And when we ended the first video, we ended on this slide. So I just want to remind you, we're talking about the vestibular ocular reflex. And if we get a head turn in a specific direction, we're going to have our eyes move opposite to that if we have our eyes focused on something of visual interest. So we have this pathway that I told you about already that starts with activity in this case, the horizontal semicircular canal, that's going to lead to contraction of the contralateral lateral rectus muscle, as well as the ipsilateral medial rectus muscle, if we're talking about this semicircular canal that we started with. What I also want to point out is that there is a circuit in place as well, so that the opposing muscles here, so the lateral rectus on the left eye and the medial rectus on the right eye, are not opposing the contraction or the movement of the eyes. And that happens because this vestibular branch of the vestibular cochlear nerve also innervates and excites an inhibitory interneuron that's going to inhibit the pathway that leads to contraction of these muscles that would otherwise oppose that movement. Okay, so now that we've gone through the circuit, we want to talk about something called nystagmus. And nystagmus is spelled like this, nystagmus. And nystagmus is defined as an eye movement that has a slow phase in one direction and then a rapid phase in the other direction. Okay, so nystagmus kind of goes like this. And it's named for the fast movement. So if we have a nystagmus that has a slow movement to the right and a fast component to the left, this would be called a left beating nystagmus. And as you can imagine, a nystagmus can be created by activation of the vestibular system. And this activation can be due to normal things or to abnormal or pathological things. So this is an example of physiological nystagmus. So this happens just naturally, and it's not because of any problem. But if you're in a car and you're driving past this row of fence posts on your right, your eye is going to naturally follow these fence posts as your car passes them. So your eye is slowly following this fence post. It's going to reach a point where it can't go any farther, and it's going to snap back and follow it again, and snap back and follow again. So that is a physiological nystagmus. So the slow phase are these tracking movements where you're tracking the fence posts in this case. And then the slow phase is going to be when you're going back the other direction to just reset your eyes. And it turns out that our visual system shuts down conscious appreciation of visual information during that reset phase, so that you don't pick up any visual information during that fast phase. You only pick up visual information during that slow phase. The slow phase, again, is controlled by the VOR, and then the fast phase is the reset. So that's physiological nystagmus. We can also have other things that can cause nystagmus. One of them is alcohol. So I told you before that if a person drinks too much, that alcohol can move from the capillaries into the cupula of the horizontal canals. That's that gelatinous mass. When it moves into there, the cupula becomes less dense and tries to float. When it floats, or tries to float, it's going to activate the hair bundles in the semicircular canal. And so this is why when you move your head in certain positions, it feels like the room is spinning. So at checkpoints, for drunk driving checkpoints, they will actually have your eyes follow their finger, because it turns out that the nystagmus is more pronounced as you move more to the edge of your vision. So as your eyes go more laterally or more medially, that nystagmus becomes more pronounced. And so that's what the officers are looking for, is for that movement of your eye, which is nystagmus caused by alcohol. alcohol stimulating the vestibular system and activating the VOR. Another thing that can cause nystagmus is if those otoconia or otoliths that are the utricle and the saccule come loose. So if you remember, the otolith organs have that otolith membrane that has calcium carbonate crystals in it, and occasionally those will come loose. They come loose if you get older, they come loose due to head trauma, they come loose if you're a neuroanatomy professor and you strike a tuning fork and show people how to do bone conduction during lab. That happened to me that night. I had a loose otolith and was extremely dizzy and probably had nystagmus. So basically what happens is these otoconia tend to drop into the posterior semicircular canal. And they hang out there, but they're not supposed to be there. So if you move your head in particular orientation, specifically if you're moving it back or turning over in bed, you're going to get a feeling like you're turning in circles, because you're going to get activation of those hair cells because the otoconia are causing that fluid to move much more than they should. Eventually, the displaced otoconia or otoliths do work their way out and become dissolved, so it usually fixes itself. And this is called benign, just because it usually does resolve itself. Proximal, so it kind of comes in waves. Positional, because it's dependent on different positions of your head. So when mine came loose, it was if I tilted my head back, but if I held my head straight forward, I was fine. And then vertigo is just dizziness. Because as you can imagine, the vestibular system, if your eyes are kind of going wonky when they're not supposed to, that's going to make you dizzy. And then we also talked about how if there's a mismatch between the vestibular system, the visual system, and your proprioceptors, that also can lead to nausea. So both the benign proximal positional vertigo as well as alcohol can make you nauseous as well, for some of the same reasons. Okay, so now what I'm going to do is going to give you a teaser to the next part. We're going to watch a video, and that video is going to show you how the vestibular system helps us or doesn't help us. So let me start this video. Hopefully you can see it. There's no sound, but you don't need sound. So this is somebody that's getting their semicircular canals to activate the VOR. Okay? So he's excited about this. He's ready. So what they do is they're going to put their head down on the bat and move in a circle. And that's so that those horizontal semicircular canals are even more horizontal. So they're getting that endolymph to move. But after a while, the endolymph's going to catch up and go at the same speed as the head. And then when they stop, it goes in the opposite direction and ends up activating extensors, and the guy's going to fall over the fence. So there he goes. So what's happening here? So let me explain it to you a little bit, and then we're going to go into the vestibular colic and the vestibulospinal reflexes. So one thing that I need to tell you first to understand what's happening is that I left out one of my slides, apparently. So let me pull this up. That didn't work. Oh, because I'm not on that. Hang on. Bear with me, people. I don't know why that disappeared, but it did. Current slide. All right, so to understand this video, you have to understand something else first. Oh, I know why, because I talked to you about this in the other vestibular video. So if we have a horizontal semicircular canal, and we have a head turned to the left, remember our vestibular system responds to acceleration, not necessarily velocity, but acceleration. So if we have a head turn, initially we're going to get that endolymph lagging and going opposite, okay? But if we have continued rotation, then what happens is in this is supposed to be the semicircular canal. What happens with continued rotation is that eventually that endolymph is going to stall, and then it's going to go in the same direction as the head. So this is with continued, we're no longer accelerating, now we're just going around in circles. And so this decreases the stimulation of the hair cells. But then when we stop, that endolymph is going to actually go in the opposite direction. So now, if we stop the head, so the head is stopped, this is going to keep going for a little bit. Okay, so because of inertia, the endolymph keeps going for a short amount of time, not forever. And so that's going to actually come around and affect those the opposite way. So now it's going to push that hair bundle towards the shortest one. So this is a deceleration, and this is an acceleration. And in the middle, we don't get as much stimulation. So in the bat video, initially they were doing this when they're going around the bat. Then they get it to this point where the endolymph has caught up and it's going with the head, such that when they stop the head rotation, we're getting that lag that's going to keep going and actually affect the hair cells with a kind of an off response. And so that's what they're responding to. And what that off response does is it's going to activate vestibular reflexes as well. And in particular, it's going to activate the vestibulospinal reflex and the vestibulocochlear reflex. The vestibular ocular reflex is also going to be activated, but we don't see that on the video. So in the next video, I'm going to go through the vestibulocochlear, vestibulocolic reflex, and the vestibulospinal reflex and explain what's happening in that video. So I will see you